professor at the University of Munich in Germany. Eric is a group leader at the Max Planck Institute related to alloys for additive manufacturing, and he will talk to us about L-PBF over ferritic steel. So please, the floor is yours.
Yeah, thank you very much for the introduction, and thank you very much for the invitation. It has been a pleasure to be back at a conference, although virtually. It's great to see you, many of you again. So yeah, as you can see here on my slide, and if you know my previous presentations also by the color change of the template, I have indeed moved institutions 1.5 years ago. So in the beginning of 2020, I moved from the Max Planck Institute for Iron Research to the University of the Federal Armed Forces in Munich. So outside of Germany and German-speaking countries, everybody is always having trouble with Bundeswehr, with this particular word, and I will say very few words about what that means. But this work here, as you can imagine, over the last 1.5 years, I've been very busy establishing a new group, fighting with purchase departments and procurement departments and building services over the new labs and so on. And we were very excited to probably do our very first L-PBF experiment next week here in Munich. All right, so the work that I will present today still comes from MPIE in Düsseldorf in Germany. And it was done completely by Hideaki Ikehata, who was on leave from his employer, the Toyota Central R&D Labs, and despite coming from industry, did the most curiosity-inspired research. So before I dig into that, and I think you know, I think it's perfect to have this talk right now, because we've heard about nucleation and inoculants. We've heard about ceramic particles and ODS alloys. And now I will be talking about basically grain refinement by ceramic particles. So we'll come full circle. Very briefly about my current employer, because if you're like me, a few years ago, you've never heard of this university. It is a weird one in the sense that it is operated by the federal government, specifically by the Department of Defense. And the reason why we exist is because our Department of Defense wanted to make the career of an officer in the German Armed Forces more attractive. So the deal is you sign up for 13 years, and after the first year, you are allowed at full pay to come and study in Munich or in Hamburg, and get a civilian degree, which will later be useful when you're done with your military career. And afterwards, you know, you go and do your thing in the army. But the courses that we offer are civilian courses. We're not a military academy or something like that. We're a small university located in the south of Munich, roughly 3,000 students. Yeah, this is where I work since 2020. And I suppose other than the fact that our students have a really a love for green clothes, it's really not that dissimilar from a normal university, I would say. Perhaps in the current context, I should also mention that right now I have an élève officier from the French army actually in our labs doing a bachelor thesis, who is on exchange here. Right, so what is this about, this talk today? This comes from my curiosity, from my question whether we could use process atmospheres in additive manufacturing, specifically L-PBF, to do something useful, to somehow change the alloys that we're working with. So here the slide is, this is old, these are old results that maybe some of you have already seen before. And this is very closely related now to Christian's talk. So I'm very happy that you already introduced ODS alloys and so on. In this particular case, we were wondering, can we use a reactive gas in order to get small nanometer, well, not really single nanometer, but let's say sub-micron sized oxides in the material. And it turns out that you have these oxides no matter if you try to have them or not. This is also exactly what we've seen in the previous talk. But if you do use CO2 instead of argon as a process atmosphere, there are way more small oxides after than before. Right, so that worked, that kind of worked. We also saw an increase in hot compressive strength. Unfortunately, we couldn't do creep tests, but about 20% increase. So we were very happy about this result. Now, the question that I was curious about is, can we also do the same thing with nitrogen? So can we somehow use an N2 atmosphere? There were some indications from previous works on pH steels that nitrogen does play a role. First thing that we did was we looked at very simple austenitic stainless steel process under argon and nitrogen. And I have to tell you, the differences are, I mean, they're there, but you have to really look very closely to find a difference. The higher the energy density, the more the nitrogen, the higher the nitrogen content becomes. If you process under nitrogen, it's the reverse when you process under argon. Yeah? But if you look at the numbers, I mean, these are very small differences. Yeah? And also, if you look then at tensile tests in the middle, yes, there's a tiny difference, but I really had to magnify this axis here quite a lot to make it visible. So we think that the main difference is that the little bit addition, the little addition of nitrogen in this case adds a bit of austenite stability, which you can see after deformation that you have less strain-induced martensite. So, okay, you know, chromium, although it is a nitride-forming element, apparently is not enough to, you know, to show a big, remarkable effect when processed under nitrogen. So let's do something else. Let's take lots of elements in our materials that love nitrogen even more than chromium. And what is that? Well, that's, for example, titanium. That's, for example, aluminum and the chromium one you've already seen before. Okay, so we work with a bunch of model alloys. I'm only showing some of them here. Later you will see a few more, but very simple alloys, iron plus X, yeah, to begin with. And we selected them for the nitride forming ability on the one hand, but also on the other hand, for their ferrite stabilizing ability. In the beginning, we did that purely because, you know, we didn't want to deal with phase transformations on top of the gas interactions that we were looking at. Yeah, so this is why we became interested in ferritic steels, because we said, well, this is as simple as it gets. You solidify full as BCC, and above a certain concentration, for example, titanium here on the left, you constrict the austenite field enough that you stay completely ferritic as you cool down. Okay, of course you can't overdo this. Yeah, if you alloy too much, at some point you will get into metallic phases. For example, in this case, the Laves phase. You know, with chromium, you could potentially get the sigma phase and so on and so forth. So that just as a foreshadowing for later. Instead of purchasing all of these model alloys from nice companies that produce good results but are a little bit pricey, what we did is to go ahead and just mix elemental powders. So we just use pure iron, pure titanium, pure aluminum powders, mix them together, and yeah, I think by now many groups are doing this worldwide, and it has been shown that if you're a little bit careful with parameter selection, in particular, you need to make the melt pool relatively large and go relatively slow. If you do that, you can get quite nice chemical homogeneity. So that worked also in this case relatively well. I'm not showing you this here, but you can see an example in this paper cited at the bottom. Right. One comment about the pure powder that we worked with. In this case, it turned out that the pure iron powder was not so pure at all. In fact, we had lots and lots of particles in there. So this is oxygen and oxide particles. And well, we learned a lesson here. In the future, we will always specify a maximum oxygen content when we buy powders. Because the manufacturer just shrugged and said, well, you asked for iron, and you know, it is iron mostly. Yeah. So this is what we had to work with in the beginning. Keep that in mind, because this will become important just on the next slide. However, later on, we purchased pre-alloyed iron 5 titanium powder, and there you see nothing, yeah, as it should be. I mean, almost nothing. A tiny little bit of oxygen is, of course, also there. Right, before I dive in, just to show you what these alloys look like, or this particular alloy, iron chromium, what this looks like if you deform it, if you process it without any additional nitrogen or what have you. The texture is very, very strong. And if you, I mean, it's not really single crystalline, of course, but essentially it behaves like a single crystal because it's a very strong texture. And if you after deformation, if you go back to EBSD, you see exactly the kind of rotation, lattice rotation that you would expect from a single crystal deformation. So this is really, for me, it was very nice to see this textbook behavior for the first time in my life as a researcher, because I've never worked on single crystals before. All right, but let's look at the nitrogen influence. We took various mixtures of iron and titanium powders. We processed them under nitrogen atmosphere, and then we just looked into the microstructure. At 2% titanium, you see perhaps some effect, but nothing crazy. You still have relatively coarse grains. You don't have quite as strong a texture anymore. But then when you go to 5 atomic percent titanium, you see quite a stark difference. You have suddenly these very small globular grains, equiaxed, almost just a little bit more than 1 micron in diameter. And a complete randomization of the texture. Yeah. In the microstructure, we have plenty of particles in both cases. So there must be a difference. Yeah? I mean, we immediately thought about particle-stimulated nucleation here. We didn't think about quasi-crystals or something, which we were just thinking, well, where are the particles that could give us this heterogeneous nucleation? And indeed, there are particles everywhere, yeah, but not only for the 5% titanium, also for the 2% titanium. The difference is actually the crystal structure. We selected the biggest of them all. So these are all, I just see that I don't have the scale bars here, but I think it is the same, roughly the same scale bar here for the EBSD and for the SEM. I will check that later. So these are all particles that are less than 100 nanometers in size, or roughly 100 nanometers in size. And if we look for a while, we also find some coarser ones, and we pick these coarser ones for an EBSD analysis, and we see, okay, in the case of 2% titanium, we have Ti2O3 crystal structure. That's an hexagonal crystal structure. And for the 5% titanium, we have actually rock salt crystal structure. So TiO, this is compatible with TiO. And TiO particles can form a specific orientation relationship, the Baker-Nutting orientation relationship with a ferritic matrix. And that is one prerequisite for heterogeneous nucleation, as we've heard before today from other speakers. We could confirm this orientation relationship in the TEM, so that all fits well. Question is, why do we have TiO in the case of 5 titanium, but not in the case of 2 titanium? And thermodynamics can give us an answer to that. We just plugged the numbers into thermocalc. So we added this 0.2% oxygen that we measured in the as-produced samples, plus X% titanium. And here on the right-hand side, you see that if you have less than approximately 3 atomic percent titanium, you get, or thermocalc predicts Ti2O3, which is exactly what we see for the 2% alloy. And then at higher concentrations of titanium, thermocalc predicts TiO. So that, thermodynamic predictions fit reality very well. That's always nice. So 0.2% oxygen, that's of course a lot. Yeah. And it's not quite as much as we had in the powder. In the powder, we had almost 0.4%. So we're losing oxygen during the processing, but it is, of course, still a very high content. We would rather like to measure this in the low ppm. Right. So I will show later again this pre-alloyed powder that we purchased in a second step, and there we have 1 order of magnitude less oxygen content after L-PBF. One more point. Look at the nitrogen content. Yeah. So the 2 lines in this table are the iron and titanium powder mixture processed under nitrogen atmosphere, under argon atmosphere, and you do see a nitrogen uptake. Compared to the oxygen, however, it's practically negligible. Yeah, I mean there is a clear difference between argon and nitrogen processing, but it is not a huge difference. All right, so to reinforce this whole point of what do you need in order to get grain refinement by particles, it's not enough to have the right crystal structure. You also need a compatibility in terms of lattice constants. And indeed, TiO, not only TiO, but also TiN and TiC, all of these phases have the right crystal structure for a BN orientation relationship, and they also have a very low lattice misfit with a ferritic matrix. This is actually from steelmaking, nothing new. Yeah? So all that we do in additive manufacturing is either already known from welding or from metallurgy or, from somebody else. So in this case also, it was well known that these, that for example, Ti2O3, Al2O3 are not or have a relatively large lattice misfit, but TiN, TiO, TiC have a very low one. Here in the from the literature, we have TiN. We calculated the corresponding values for TiC and TiO here on the right-hand side, and you see that TiO is indeed the one with the lowest misfit, but also TiC and TiN should be effective grain refiners. And given the fact that we have some nitrogen uptake, possibly we have some TiO, N as well. I mean, the mixed oxynitride is known in this system as well. So that is, this is something that we possibly have in the system as well. All right. Once again, it's not only the number of particles, it is the type of particles. I mean, I think I've said this now 5 times, but one more time here, and a little bit more quantitatively. We have some. We've tried some alloys that are completely full with oxide particles. I mean, this looks very nicely like an ODS steel, right? This is iron vanadium. And vanadium is an element that, of course, likes to react a lot with oxygen and nitrogen. So the powder that we purchased was probably like 50% vanadium oxides and 50% vanadium. And after processing, you have tons and tons of particles, oxide particles, but no grain refinement. Why? Because you don't have the correct type of oxide. And here on the left-hand side, you see that our oxide diameter and number of particles or volume % of particles is not really what's determining grain refinement. It is the type of particles. Okay. So so far what we've seen is basic. I mean, a little bit of nitrogen, but basically the oxygen that was already there in the dirty iron powder, and that gave us the grain refinement as soon as we had the correct amount of titanium that allowed the formation of TiO. Of course, the question is, if we know that TiO and TiN are responsible or are effective in grain refinement, well, can we just take them and throw them into the material in a powder mixture? And we specifically did not do the careful and nice work that Christian just presented, in the sense that we took nano powders and we ball milled. No, we didn't do any of that. We just purchased some micron size TiN powder, TiC powder, TiO2 powder, and we just threw it in and saw what happened. And in fact, so on the left-hand side, you see iron 10% aluminum and iron 2% titanium. We see relatively coarse grains. And then as soon as you have a TiN and TiC addition, you do have strong grain refinement. And if you if you add TiO2, you do not have grain refinement. And that is understandable because the phase predicted at 2% titanium is Ti2O3, or perhaps the particles remain Ti2. I don't know, to be honest. But in any case, you do not get grain refinement. In this case, here in the middle, with TiN and TiC, you do get grain refinement. And just to add to the discussion that we just started about does the yttria dissolve or not? This is the microstructure of the material after L-PBF processing. So here at the bottom, you see that most of our TIN particles are 1 micron and above. And afterwards, none of them are even close to 1 micron. And TIN is a material that has a melting point. I just checked Wikipedia just before my presentation, nearly 3000 degrees C. So I would say apparently in the melt pool, there is enough thermal energy to somehow make these TIN go from several micron to maybe 100 nanometer. My guess is they melt. It doesn't look likely, yeah, with a melting point of 3000 degrees, but I think that's what's happening. Of course, I only have this indirect indication here, but this fits very well with actually a lot of powder mixtures of ceramic particles that we've tried over the last years. Okay, so this is another slide that I only put in here because it fits well to what we've heard earlier today. So this is an ODS steel. So this is powder that you can buy from Ecole, iron 24 chromium, 8% aluminum, 0.3% yttrium, which is basically 0.5 volume percent of Y2O3. And, you know, we just took this powder. It should be fully ferritic. And it is, you know, if you just take the base alloy here on the left-hand side, it is fully ferritic, coarse grains. And then we threw in titanium carbide. At first, you generate cracks, which is not very nice, of course. And you find a lot of precipitates along grain boundaries, presumably titanium carbide or some other carbides, I don't know. But if you add enough titanium carbide, in this case 4% volume percent TIC, you go to a very nice fine-grained sub 1 micron grain size equi-exed microstructure. You have tons of these fine precipitates, and you don't have any cracking problem anymore. So on one slide, I have managed to tie together 2 of previous talks from this morning and this afternoon. Okay. But let's go back to our model alloys for a moment. Of course, if you've discovered an effect, you want to know, hey, can I make it even better? So can I throw in more titanium and more titanium? So we also looked at 7.5% titanium and 10% titanium. And in a sense, yes, you can make it even better. Yeah, so you can go from a bit more than 1 micron diameter to less than 1 micron diameter. But with 10% titanium and already with 7.5% titanium, it becomes very obvious that you're not only generating oxides and possibly nitrides, but you also have a ton of Lavis phase in the microstructure. And Lavis phase is typically considered a very brittle phase. I mean, we didn't do a tensile test on these materials, but I cannot imagine that this microstructure that has significant amounts of Lavis phase gives you a very nice ferritic steel. So we did not follow this. Sorry about that. We did not test this further. Okay. But let's now go back to the 5% titanium, which we know works and where there's no Lavis phase, and go back to the very initial question of my presentation. Can we use the process atmosphere to change something in the microstructure? And with our initial experiments, I already told you, well, there's a little bit of nitrogen uptake, but it doesn't matter. Why? Because the TiO coming from the dirty powder is what's giving us the grain refinement. This is where the clean powder comes in that we purchased from a different company, and where we have only very little oxygen content in the beginning. And in fact, now we see an effect of the atmosphere. We do see, I mean, we still see a lot of grain refinement in the case of processing under argon, yes. So here you have a kind of a bimodal microstructure with some elongated grains and columnar grains. And of course, these are definitely much finer than, for example, this microstructure over here with the 2% titanium. But you see a difference. Yeah, you don't have complete grain refinement as in the case of processing under nitrogen if you process under argon. So, you know, given that it is much easier to just purchase some titanium nitride micro powder and throw it into the mixer, into the blender, you could question why we need this gas reaction at all. But I still think it's a neat idea on the one hand, and on the other hand, it of course makes your grain refinement switchable with one and the same material, or at least to some extent switchable. Yeah, you could imagine processing parts of the material under nitrogen and other parts under argon, and then you could go from more or less elongated grains to equix grains if you desire this change. Yeah. Okay. So to come to some, I mean, this is a Euromechanics colloquium. Yeah. So a little bit of mechanical results I should also show you. So we wanted to compare material with and without grain refinement. The comparison is always a little bit difficult because we need to add this large amount of titanium. So you always not only do grain refinement, but you also alloy titanium. We first started with a martensitic stainless steel, which is a commercial powder you can buy, basically 13% chromium and 4.4% carbon. We tried it out. We did get a lot of grain refinement. The problem is that probably a lot of the carbon is now bound in carbides if we add so much titanium. So we thought comparing this before and after addition of TI is probably comparing apples and oranges. So we went back to our very boring model alloys. Well, you could say it's a commercial ferritic stainless steel, but in fact, it's just a binary iron 19% chromium alloy. You've seen this before. This is the quasi single crystal behavior. And if we add now 5% titanium, the grain refinement in this case comes again from the dirty iron powder. You see the stark difference in microstructures. You see the stark difference in texture. And we now produced blocks of these two different materials, machined tensile test specimens out of them, and looked at the results. And the result is, yes, there's a significant strengthening, quite a lot of strengthening. I don't need to to play tricks with this y-axis here at all. You can immediately see that there is a big difference. Yield strength is going up, UTS is going up. Unfortunately, elongation is going down. Yeah, so we do the usual trading of ductility for strength. But it is quite a significant increase in strength. I mean, it was something. Now, of course, as I just said, this is not only the grain refinement. We're adding 5% titanium. So this is in fact a different alloy. We try to do a kind of a back of the envelope calculation to see how much of the strengthening we see is due to Hall patch strengthening. For that, we assumed that we have more or less the same number of and dispersion of particles in the alloys. Yeah, so we could say this is roughly the same. We estimated the texture effect just by the Taylor factor, and then if we subtract from the overall strengthening and we also estimated, of course, the solid solution strengthening from a paper that we found. Now, probably overestimating the effect of solid solution strengthening because some of the titanium will be bound in titanium oxides. But, as I said, just back of the envelope type of calculation here, in the end, you see that roughly half of the strengthening that we get is from making the grains, roughly 1 micron in size instead of many millimeters. Okay. So we're still not going to win a lot of awards with this model alloy. I mean, if we plot this together with lots of different other steels and stainless steels, then you see that we go from abysmal to unremarkable in mechanical properties. So if you are in industry and you want a material, just go ahead and buy PH steels, I would say. But from the academic point of view, it was a very nice study, I think. For us, at least, it was fun. And in the end, it was a binary respective ternary model alloy. Okay, so to conclude my talk, we could see that that dirty powder gives you sometimes nice results. Yeah. So in this case, we have Ti O, N. as heterogeneous nucleation sites in ferritic steels. You need to add enough titanium to get this in situ, or you add it ex situ. In other words, just throw in TIN powder. And you can also do it with my my hobby of switching gas bottles in L-PBF processes. That also works if you're careful. We see, of course, a strengthening due to grain refinement, but unfortunately, we pay a little bit with ductility decrease. And with that, I have to thank Hideaki and his employer for the 2 years that he spent in my lab. And if you want to read much more about this, you can have a look at this series of 3 papers that came out, all of them this year, where he wrote all of this up. And I will also post this in the chat in a moment. Thanks very much for your attention.
Thank you so much. Really nice presentation indeed. Nice things to think about, changing the gas bottles, and well, good ideas there, and probably to be pursued to get better properties. So do we have questions around here? I see Christian has one. Please.
Yeah. Thank you, Eric. Very nice work indeed. I like it. Did you check whether you can control the uptake of nitrogen, so the amount of nitrogen that you have in your material, by, well, playing with the melt pool lifetime? I think you remember our work where we did the opposite, so degassing that. Do you see an effect also in the opposite direction?
Yes, we did, and so we didn't do this very systematically. In this case, we studied much more the alloy systematically, but not the processing parameters. However, I did challenge Hideaki once to see, okay, if you not only melt the powder once, but if you really like take the laser and barbecue one particular position for a very long time, can you get a lot of nitrogen uptake? And in fact, you can. So I have a slide somewhere in the backup here. So if you remelt the surface many times, I mean, I didn't put this in the presentation because this is yet again another alloy. This is a Simar aging steel. But you could really see if you remelt 10 times or something, you start to get really coarse nitrites. Really coarse nitrites. And up to the point where you know, they become nicely detectable in EBSD. So I can only assume that you can indeed play with the process parameters and get more or less of these nitrites.
Thank you.
I see Teresa has a question.
Yes, thank you very much, Eric, for the talk. Just one quick comment that one of my alma maters is the Naval Postgraduate School in Monterey, California, which seems very similar to the university you are in. So I learned TBSD there, and it's a place that I remember very, very fondly. It reminded me a lot when you were describing your university. But my question was, when I was looking at your fine-grained samples, I was immediately thinking about the grain boundaries. No? So I don't know if you took a look at the grain boundary distribution for these very, very fine samples. Very fine.
I didn't. But of course, I mean, during your talk this morning, I posted immediately in our group chat that henceforth I will look at, for every alloy, for every EBSD scan, I will look at the misorientation angle distribution. I have not had a chance to look at it here. Okay,
I'd be curious to know when you find out.
For sure.
Thank you.
Okay, that's the aim of our colloquium, is to make new ideas, build new ideas, and also maybe make new interactions between teams. And so don't hesitate to. This is a hard way of ensuring some interaction, but however, I hope this will initiate new things between European groups, and hopefully will end up in nice projects that we can hear of in the future. Do we have additional questions? I guess these ones are forgotten. Roland?
Yes, Thanks a lot. I mean, really interesting ideas that you bring up. I was just wondering concerning, I mean, this is the complementary question to Christian in a sense. So you can play on the laser parameters to change the reactions, but have you tried also to play on the gas flow, on the pressure, for example, and to see if you can increase or decrease the reaction rates?
No, I haven't. But that is indeed something I was also thinking about that. Yeah. Contrary to what some people are doing in L-PBF, where they go to lower pressures and then to do L-PBF under partial vacuum, here it would be very nice to do it actually under high pressure. As far as I'm aware, there is only one machine in the world where people, and that is at MIT, I think, with John Hart, who did a high pressure L-PBF machine. And I don't even know if it is still operational or if they just disbanded this idea. So in our machine, we can only do like maximum 100 millibar overpressure. So
oh, I see. Okay.
Yeah, we thought it's not worth doing it because probably the effect is not big enough. If you look at high nitrogen metallurgy, I mean, you need like many bars of overpressure, right, to see a big effect. But yeah, it should make it should have an effect. It definitely should have an effect, and it would be interesting to study. Now we did in the case of so here we were just very simple. We just switched from nitrogen to argon and back. So that was very, very simple, the experiment. In the case of the CO2 study that I mentioned in the very beginning, we did indeed change the oxygen partial pressure. So we had argon plus various different CO2 partial pressures. And we first started, very, very carefully, argon plus 2000 ppm of oxygen. So that's 0.2% of oxygen. Because we were really afraid and basically nothing changed. And then we took 2% of CO2, still nothing happened. 8% of CO2, small effect. We started going to oxygen contents higher than the powder oxygen content. And then I said, okay, forget about it. Let's take the bottle with 100% CO2. And that was actually the most interesting one.
Okay, yeah. I mean, because, for example, in our lab machine, you have a vacuum pump and at the same time you inject, so you could actually vary
yes.
the amount in that way. So that's one possibility also. Yeah, thank you.
But would that maybe impact in some way the flowing or the deposition of the powder? Because you might have like an effect on the powder deposition to have like a high flow, right?
I think the powder deposition would probably still be okay. I think that is slow enough that the question of gas pressure is probably not so affected, but definitely it would strongly affect the process. I mean, you basically go to conditions that are a little bit similar to EBM, where you operate under a vacuum, so you get a lot of material evaporation. I remember vaguely works from the lab of Christian Caudet, who did this some years ago to do L-PBF under vacuum or under lower pressures.
Yeah, I didn't mean under vacuum, but you can play actually by putting neutral gas and then do a little bit of pumping at the same time.
In fact, researchers at Linde, not very far from here, in the north of Munich, they're of course looking at because they want to sell us beautiful gas mixtures. They have a machine where they have a gas mixing device in front of it. So there you can go ahead and get specimens with all different gas mixtures of argon, nitrogen, helium, and with all different combinations. They don't have CO2, I asked them, and they were not really looking into that. But at least when it comes to these different mixings, they're interested in that.
Thanks.
Thank you very much. I had a small questions about the ODS alloys, the creep properties. So you didn't test them yet, I understand. Well, is that going to go into the right direction in terms of volume fractions and so on?
I'm not sure. I'm not sure if this is going in the right direction. I mean, it's not terribly far away. Also in terms of size. As Christian mentioned, of the commercially produced ODS alloys, some of them, like these 9% chromium mechanically alloyed ones, they have really tiny oxides, a few nanometers in size. We don't have that here. Yeah, we have the smallest oxides that we have, and this also holds for the nitrides that we generated in this study that I presented today. The smallest ones are in the order of a dozen nanometers, roughly. So you can still see all of them in SEM. So yeah, this is going roughly in the right direction. Smaller would be better. Volume fractions is also going in the right direction, possibly not there. The big point is, of course, matrix grain size. Yeah, so exactly what Christian just talked about, that you need the dispersoids, but you also need large grains. Yeah, so you need to do this solution annealing, i.e. recrystallization, and then you want as large grains as possible. Exactly the opposite, of course, of what I just showed here. Yeah, where we have tiny grains. So yeah.
So there's still some work to do, but that could be interesting for this field that is definitely having processing issues.
Yeah, for sure, absolutely. Yeah.
Okay, I guess we need to move on time-wise, and thank you very much for this interesting presentation, and good luck with installing your new team and things.
Thank you.
So